In this video, we will build a bidirectional logic level shifter. It's a clever circuit that links 3.3 volt and 5 volt signals using just one small MOSFET transistor and two resistors. I will first explain exactly how this clever circuit works. Then we will build it. I will put it on the bench for some practical measurements to check its limits. And finally, we will see it in the real application. Now, I've also seen a version of this circuit online made with an NPN transistor. At the end of the video, I will show you that circuit and explain why I do not recommend it. Now let me start by explaining how this clever circuit works. Here's the 3.3 volt side and here's the 5 volt side of the circuit. The low 3.3 volt signal is connected to the higher 5 volt signal via this MOSFET. Now let's see what happens if the 3.3 volt signal is high. If this signal is high, the gate and source will be at the same voltage. So the MOSFET is off and the 3.3 volt and 5 volt signals are disconnected. The 5 volt signal will be pulled up by the 4.7K resistor to 5 volts. So the signal at 5 volt side is high, the same as the 3.3 volt side. Now, if the 3.3 volt signal is low, the source is pulled down, so we will have 3.3 volt on the gate. The MOSFET turns on and pulls the 5 volt signal down to the ground. So the 5 volt signal is low, the same as the 3.3 volt signal. Okay, but now it becomes interesting. What if we apply signals at the 5 volt side? Well, if the 5 volt signal goes low, the 3.3 volt signal is first pulled down via the internal body diode of this MOSFET. Now you may think we will get 0.6 volt here because of the diode voltage drop. Well, that would be quite okay already, but it gets even better. Because the source is pulled down, we will again get a positive voltage on the gate of 3.3 minus 0.6 volts, which is about 2.7 volts. Still enough to turn on the MOSFET. The MOSFET channel will start to conduct, and yes, that also works in reverse direction. So we really get 0 volts here at the 3.3 volt side. Cool, right? Now what if we have a high signal of 5 volts at the 5 volt side? Well, the diode will not conduct because this voltage is higher. So the MOSFET is off and the 3.3K resistor will pull the 3.3 volt signal to DC 3.3 volts. So the 3.3 volt signal is high, the same as the 5 volt signal. Well, that was enough theory. Let's now build it and test it. I built two of these circuits on one PCB so I can mount it on a solderless breadboard for later. Now let's first test the circuit converting a 3.3 volt to a 5 volt signal. For the test, I connected the input to an ESP32 PWM generator and I checked the output signal with an oscilloscope. Now let's connect it all together and see how it works. Here we have the circuit with a 3.3 volt 1 kHz signal on the input, which is the yellow trace. And the green trace is the 5 volt output. So this works. 3.3 volt in and 5 volt out. The signal is a bit noisy because of the long breadboard wires. Now let's increase the frequency. Change the time base. At 100 kHz you already see the upgoing ramp has a slope. This is the current limitation of the 4K7 resistor, but it's still okay. Now let's try 500 kHz. So now the slope is very clear. This may still work, but it doesn't look so good. Now let's go to 1 MHz. Now at 1 MHz the signal is clearly distorted. It might still work, but it doesn't look reliable. So this circuit can work well at 100 kHz or 200 kHz. You can go higher, but you will need to reduce the resistors. For instance, 1K for the 5 volt side and 680 for the 3.3 volt side. Now let's see how it works in the opposite direction, from 5 volt to 3.3 volt side. To test the circuit converting a 5 volt to a 3.3 volt signal, I connected the 5 volt input to an Arduino Nano PWM generator and I checked the output signal at 3.3 volt side with an oscilloscope. Now let's connect this together and see how it works. So also in reverse, this circuit works very well. 5 volt in, 3.3 volt out. Now let's increase the frequency again. Change the time base. Also in reverse, you see at 100 kHz that the upgoing ramp of the 3.3 volt signal has a slope. But the signal is still okay. Now let's go to 500 kHz. So the signal might still work, but it doesn't look that good. Let's go for 1 MHz. So at 1 MHz you see the signal is clearly distorted and it doesn't look reliable. So as mentioned before, this circuit will work well at 100 kHz or 200 kHz, but if you want to go higher, you will need to reduce those resistors. So the circuit can convert logic signals in both directions up to a few hundred kHz. The speed limit depends on these resistor values. So if we want to be faster, we can reduce those resistors. By the way, I included some LT-SPICE simulation files in the description so you can simulate the circuit. Now let's test the circuit in the real application. To test the circuit in both directions, I sent data packages of 1 kilobyte from an ESP32 at the 3.3 volt side to the Arduino at the 5 volt side. The Arduino will receive the data package and send it back to the ESP32, which will check if the data packet is still correct. We use the UART2 of the ESP32, so we can monitor the number of successful packages it received via UART1, which is connected to the serial monitor of my laptop. This is what the test setup looks like, and yes, debugging took some time. Now let's power it up and see what the limit of this circuit is in the real application. Here we have the test running at 500 kilobaud. Communication is still reliable. As you see, I already sent 2700 packets without any fails. The green trace here is the RX of the Arduino. The signal still looks good. Now let me have a look at the RX of the ESP32. Channel 1. Here you see clearly a slow ramp, and this will define the limit of the circuit. I tried, and the circuit will fail at 1 megabit. About 3/4 of the bytes are wrong. Actually, 500 kilobaud is still better than I expected. Now at the start of the video, I mentioned there is another version of the circuit based on an NPN, but I do not recommend it. Let me explain how it works. If the 3.3 volt signal is high, the base is shorted to the emitter, so the transistor is off, and at the 5 volt side the 4K7 resistor will pull the 5 volt signal also high to 5 volts. So far so good. Now if the 3.3 volt signal is low, the emitter will be pulled to the ground. Now a current can flow into the base and the transistor will switch on, putting the 5 volt signal low. Also okay. Now let's see what happens if we turn it around and have a signal from the 5 volt side. If the signal at the 5 volt side is low, a current will flow from the base, which is 3.3 volts, to the collector, because this is also a PN junction and it works like a diode. Now the transistor will work in reverse active mode. Yes, you can use the collector as an emitter, but with very poor performance and a very low current amplification. So the transistor will switch on and the 5 volt will be pulled low. Still okay. Now if the signal at 5 volt side is high, the collector is higher than the base, so the transistor turns off. But it needs a little time to switch off, so you will get a short 5-volt peak at the 3.3 volt side. Now this is a real problem. We make a level shifter to protect our 3.3 volt microcontroller, but we still have 5-volt peaks. I built this circuit so I can show you some signals explaining why I do not recommend it. Here you see the circuit working at 9600 baud. It is the same setup as I used for the MOSFET version, sending packets between an ESP32 and an Arduino Nano. You see here that the communication has no problems. So that looks good, right? Well, let's have a look at the signals coming from this level shifter circuit. The yellow trace here is the 5-volt output of the level shifter connected to the RX of the Arduino Nano. It looks good at this scale, but when I zoom in, you see that the transistor causes some switch delay. It's about 800 nanoseconds. Now let's have a look at the signal coming out of the 3.3 volt side. Trigger on channel 2. Now here we see a critical problem. The circuit overshoots the 5 volts and slowly goes back to 3.3 volts. So what's happening here? Well, the transistor cannot switch off instantly. It needs some time to lose its charge carriers. Now if I add a 1K resistor from the 3.3 volt output to the ground, it becomes clear. Here we see a very short peak. Let me zoom in. So the transistor causes a very short 5 volt peak, which is quickly absorbed by the 1K resistor. Now, the ESP32 does not fail. But how long can it last? 1 hour? 2 days? 1 year? Nobody knows. So this is very risky. The circuit seems to work fine, but we cannot guarantee it. So this MOSFET logic level shifter is a very clever circuit and can transfer signals from 3.3 to 5 volts and back. It works well up to 500 kilobits, and you can further speed it up by reducing the pull-up resistor values. Because it's bidirectional, it is very flexible. You do not need to consider the data direction in your hardware design. Now of course, for 5 to 3.3 volt, you could just use 2 resistors and save the MOSFET. I hope you liked the video. If it was useful for you, please like and subscribe. And leave your experiences in the comments.